Happy to have another opportunity to present another aspect of my work. So this topic of magnetic reconnection is important in many different research contexts. And I got the opportunity to work on it while I was at MIT. My collaborators are Nunu. The work that I'm presenting today is mainly done with him. I have done another thing which is related to inverse cascades and so on, which I'll not be talking about today, but that is something that I've done with Mooney and Dimitri. So reconnection here is a simple physical picture of how reconnection takes place. So there are these oppositely directed magnetic field lines being brought together. And just here at the point of reversal, there is a current sheet. And these field lines get to diffuse through the current sheet and reconnect. And as they reconnect, they move out of the site of reconnection due to tension. So this is a kind of a steady state picture of how this reconnection is taking place. So the outline for today's talk is the following. So I've already sort of introduced you to how reconnection happens. I will describe it via a simple model. Then I want to talk about the latest major development in this field of reconnection known as the plasmoid instability. Then I will introduce you to the mother of plasmoid instability called the tearing mode instability. I want to take you through some of the derivation of how this instability can be derived and show you some of the basic results, because that will kind of form the basis of understanding how plasmoid instability manifests. Then I want to show you what is known as magnetic reconnection phase diagram. It's a bird's eye point of view of looking at different plasma regimes in which magnetic reconnection manifests. Then importantly, I will come to the core topic, which is plasmoid instability in semi-collisional regime. This particular regime is an experimentally accessible regime. Then I'll take you through some of the simulation results, which basically validate the semi-collisional regime in this phase diagram. Then I'll summarize and provide some future directions. So Sweet and Parker introduced the first ever model of reconnection in 1956. So this is a 2D model in steady state. So here's the picture of what is going on. We have oppositely directed magnetic fields, and there's a current sheet in between. And this current sheet has the dimensions of 2 delta and 2L. And we can get an estimate of the reconnection rate from following considerations. So from mass conservation, the velocity of the flow that is going into the current sheet into the length of the current sheet is equal to the outflowing velocity into the width of the current sheet. Then there is Ohm's law, and from energy conservation considerations, we get that the outflowing velocity is equal to the Alphen velocity, where the Alphen velocity is proportional to the incoming magnetic field. So inside the current sheet itself, there's a resistive layer where the resistive term in the Ohm's law becomes important. And outside the resistive layer, the other term remains. So we basically match these two solutions. And along with the other constraints, we arrive upon the reconnection rate. And this reconnection rate is a dimensionless reconnection rate. So it is given by what is known as this Lundquist number. So this S is Lundquist number. This Lundquist number is basically like magnetic Reynolds number, except in the magnetic Reynolds number, you would replace the velocity with the Alphen velocity here. And the Lundquist number is typically really large in most astrophysical systems. So like in the sun, where also the magnetic Reynolds number is very large, the Lundquist number is large, like 10 to the 12 or something. So this resulting reconnection rate is going to be really small in the sun. So if you put in the numbers, you get the time scale of reconnection on the sun. So in the sun, you can have these solar flares, which come from reconnection and so on. So if you look at the time scales on which they operate, they're happening on minutes time scales, whereas the reconnection rate estimate gives you a time scale of 2 days. So there's a huge gap between what you get from the model and what so I would estimate the S, the Lundquist number, and then I would multiply it by the Alphen time scale, and that would give me the reconnection time scale. Eta is the resistivity. So that's inverse of conductivity. So, yeah.
It's defined as the time over which magnetic field in a certain region. And how you told that you can estimate the time scale this way. What's the basic definition of that time scale? It's a quantity divided by the rate of that quantity. That way, what is the connection? How is the connection time scale defined?
I mean, it's the rate at which.
The way you have defined it, it's a dimensionless thing. I don't think of rate as a dimensionless quantity. In the reconnection rate and it.
So, because this is a steady state model, there are these magnetic fields being brought in continuously, and they are, it's being, I mean, reconnection happens, and then it's being taken out of the reconnection site. And the dynamical time scale in this problem is being provided by the Alphen time scale. So, as let's say L by V, the length of the current sheet by VA would be my dynamical time scale. And we are comparing what is the rate at which this reconnection is happening compared to that time scale.
Is that a measure of the time inverse of the time between two reconnection events? The entire object, or what is it?
Well, the reconnection event itself is happening on certain specific time scale that's given by this estimate. But the dynamical time scale could be much faster. And what we see is that because it is proportional to s to the minus half, it is actually much slower than the dynamical time scale. That's what I mean to say.
So this velocity that you have is the velocity of the plasma.
Yeah.
So is the current, and not only in a fluid, I would say the current is like velocity.
No, density, the density is like current density, which is, I mean to say the current density is basically like the curl of the magnetic field. So that is not related to the velocity. I'm not sure.
But this, isn't it the charge, like the charge current? Is the charge current?
Yeah, so it's for the electrons, whereas you can think of this velocity is the velocity for the ions. Ions, yeah. Where this J comes from, or sorry, or this V cross B. So yeah, so if you were to do, like I was telling you the other day, if you were to come from basically distribution functions and then do closure, and then you get two fluid kind of equations. Then you would take the equation for the momentum equation for the electrons, and you would have this this figuring in over there, and from that you are getting the Ohm's law actually, and the equation for the yeah.
So I think the confusion is that Ohm's law is J equals sigma E. People who are sort of electrons in a condensed matter system are used to that. What is this V cross V by C that appears next? That's the question.
Yeah, so that's just the Lorentz force, which is also kind of providing this what do you say, extra sort of electric field type of a thing for the current. I mean, basically, it is telling you how the what do you say, the electrons are moving in the once you have the given magnetic field, right? So that is also going to come into the Ohm's law essentially. I mean, I don't know if
the electrons are extremely conductive.
Yeah.
If sigma is infinite, you can get rid of the J by sigma term, right? That's the ideal image.
Sure.
Right?
Sure.
So E plus V cross V by C is E prime, which is electric field in the frame of the fluid.
Right.
So you're just saying E is equal to 0 in the frame of the fluid. That's one way of
looking at it. Yeah.
This is coming from the momentum equation, like you're taking dV dt 0 and
Right.
finding the electric field, right?
Yeah.
So this is a two fluid.
Yeah. You can get the Ohm's law from the electron. Yeah.
Do away with the dV dt.
Right. Yeah. So that is the typical picture. Yeah. Maybe we can discuss this later. So magnetic reconnection is kind of important in many different contexts. Apart from astrophysics, there is also space and there is laboratory. So in the space, you have these magnetospheric substorms, and then there's also solar flares. So I was describing this to Rama. I think I should describe it. So for example, in the sun, you have these magnetic field activity, right? So then there are these what is known as Parker instability, and there are these buoyant magnetic flux tubes which come from a lower part in the photosphere and come up on the surface, and they carry the plasma along with them. And as they come up, they can kind of get twisted or whatever and interact, and then they pinch off due to magnetic reconnection taking place, and this plasma then gets thrown out into the atmosphere. This is known as the solar flare. So people think that magnetic reconnection is underlying this particular phenomena that's happening on the sun. So reconnection is important for solar flares. Also, more recently, people think that it can be used to model particle acceleration jets and pulsar winds. There are many different models you can have, like shocks and so on, but people have found that the latest manifestation of magnetic reconnection is very efficient in particle acceleration. And people are trying to even use it as a model for gamma ray bursts. And in laboratory, like in fusion experiments, you have these what are known as sawtooth crashes, which can be problematic for the stability of the magnetic confinement, structure. So that is thought to be also arising from magnetic reconnection. So for a long time, steady state models of reconnection have ruled the roost. And despite putting many more ingredients on top of it and taking into different plasma regimes, it has been unsatisfactory in explaining most of the observational phenomena. But recently, this plasmoid instability has brought about a paradigm shift in this reconnection research. It is the latest thing which kind of seems to have solved the time rate problem, which is what I explained to you in the previous slide. So I will talk more about plasmoid instability now. Originally, it was derived by, formally derived by Lorero et al. And what they did is to take this kind of model where you have a current sheet, and there are these, again, oppositely directed magnetic fields, and there are also flows in the system. The difference from the previous picture that I showed you is that the dimension of the current sheet here is of a particular dimension. It is of a Sweet-Parker scaling dimension. So these are really thin current sheets that I'm talking about. So what I mean by Sweet-Parker scaling is that the width is given by delta CS, which goes as, okay. So these are some really thin current sheets. And so then if you introduce perturbations to the system, then it goes unstable and it forms these plasmoids. So what are plasmoids? They are basically magnetic islands. So these red things over here are signifying formation of plasmoids. And if you do the calculation, then you find that the growth rate of this instability goes as Lundquist number to the power of a positive fraction, as opposed to the Sweet-Parker model where it was a negative fraction. And this means that for a large Lundquist number, it is going to be really fast. And of course, you can get what is the wave number of the fastest growing mode. And this delta N is basically the inner resistive layer that I was talking about. And I will talk about in some time again. So Bhattacharya and Huang, they found that in the saturated steady state of this reconnection, the reconnection rate becomes independent of the Lundquist number. So this was like a major finding. The other thing that I should tell you is that the critical Lundquist number for this plasmoid instability to occur is really large, like 10 to the power of 4. So in many of the previous simulations, people had not seen this plasmoid instability because you really need like large Lundquist numbers for this to occur. And so that's why it is more of a recent discovery. And you can see that below 10 to the power of 4, the Sweet-Parker kind of scaling prevails, and it's only above some critical Lundquist number that your plasmoid instability occurs, and then it becomes independent of the Lundquist number and so on. So I wanted to show you some manifestations of this plasmoid instability, pictures of them from different simulations. So these are pictures from MHD simulations. So what happens in these simulations typically is that magnetic flux is being fed continuously to this current sheet, and this plasmoid instability occurs and leads to formation of all these magnetic islands, and they come in various different sizes, and they flow out of the current sheet as they are forming. And this is kind of a dynamical system in that way. And not only in MHD, you can see this also in kinetic plasmas, in PIC simulations and so on. This particular one is in fact the simulation which has looked at this kind of reconnection as a model to understand particle acceleration. And then they claim that this is actually more efficient than what one gets in collisionless shocks and so on. So the one thing that I want you to note is this particular reconnection is characterized by the fact that there are multiple points of reconnection, as opposed to the Sweet-Parker case where you had reconnection happening only at a single point. So it's also known as the multiple X-line reconnection. Yeah. So you continuously drive it from the boundaries. but the boundaries are sufficiently far away from the current sheet. So what decides the reconnection rate is the current, what's happening at the current sheet and not at the boundaries. So it's like, so you're kind of continuously like basically feeding in magnetic field at the boundary. I'm not sure exactly what kind of boundary conditions they used, but the idea is that there's a source at the boundary condition.
It's like if I feed into shear.
Right. Here, it's not like that. It is simply that you are providing magnetic field at the endpoints. So it is never going to zero, and that feeds into the.
What about velocity? Like, is velocity supposed to be Vn, or is it like outflow one? It can be whatever it wants to be.
Yeah, it can be whatever it wants to be. Yeah, yeah, yeah. So there's a current sheet here in all of them. So in between the domain, there's a current sheet. What is plotted is the contour of the magnetic flux, the contour lines of the magnetic flux. So you can kind of see, I mean, of course, they're going to be really large at the current sheet because of the concentration of the magnetic flux at the current sheet due to the formation of plasmoids. So you kind of see that in this case, for example, and then, yeah, so essentially it's the magnetic flux. Yeah. So these plasmoids interact, they merge, they coalesce, then they exit the current sheet eventually. So it's typically these simulations are such that they keep going on continuously. There's a continuous formation of plasmoids and they eject and so on. Yeah. So the attractive thing about plasmoid instability is that it is time dependent and bursty. So which is useful to understand a lot of the astrophysical events that I mentioned to you earlier on. So like solar flares and so on. You don't always, I mean, steady state models will not be so interesting to apply to understand these events, whereas the plasmoid instability has a time-dependent nature built in. So now I want to talk about the tearing mode instability, which I call the mother of plasmoid instability, because essentially what is happening there is some sort of tearing mode instability of thin current sheets. So the tearing mode instability can be derived in the following way. So you again have these reversing magnetic fields, and there are no flows right now in the system. And then you introduce perturbations on top of it. So what happens is that the magnetic flux is brought in, the flows get set up such the magnetic flux is brought in, and then you form these magnetic islands. And so basically upon introduction of perturbations, it goes unstable, and as it goes unstable, the magnetic reconnection takes place, and the magnetic flux gets concentrated into form of islands. So yeah, so this was basically derived by Firth-Kill and Rosenbluth in 1963. I kind of want to take you through some of the derivation because it's interesting and it could be insightful to understanding how this happens. So this is the tearing mode. So to make a tearing mode analysis, the equations that we are going to consider is the induction equation and the momentum equation. So here I've uncurled the induction equation to get an equation for the vector potential. Okay. And of course, this is the momentum equation. But since we are doing a 2D model of all of this, I don't have to work with these equations. I can reduce it into a stream function kind of formulation. So since I'm keeping only bx and by, suppose, then I retain only the z component of the vector potential here in the induction equation. For the momentum equation, what I will do is take the curl of it and get an equation for the vorticity. And then again, since I'm going to have only Vx and Vy, then I'll get only the Z component of the vorticity. I'll keep only that. So this psi over here corresponds to the Z component of the vector potential. And, and this del square phi is your Z component of your vorticity. Okay. So basically Bx is going to be minus del psi by del y, and By is del psi by del x. And similarly for Vx and Vy. So these are the equations that I'm going to work with, right? And the bracket here is, So the J is here, right? So it is it's del square of psi. Sorry? Yeah, it's a del square of psi. So eta j is eta del square of psi. I mean, again, j, you get only jz, right? So, right, so I have, so these brackets are basically Poisson brackets. So now what I want to do is take psi with psi equilibrium, which is my magnetic field, equilibrium magnetic field, and top of it I'll put perturbations. Again, there is perturbations in psi. This psi equilibrium corresponds to this, this form of equilibrium in the magnetic field. So B naught is the amplitude and f of x is some function which will give me these reversing magnetic fields. So I can take, for example, tan hyperbolic, right, which will give me reversing magnetic fields. The form of perturbations that the solution that I'm looking for is of this form. So there is psi 1 of x, and then there is a mode which is growing in y, and the growth rate is given by gamma. And these are the linearized equations from the equations that I showed you previously. The important definitions here, which I use then to restructure the equations, are the following. There is tau eta, which is the resistive time scale. Here I should now draw like the magnetic, okay, the configuration. So I have, yeah, my lines are terrible. So this is the reversing magnetic field, and I'm going to take a like visually broad enough current sheet, but it's going to be a, yeah. So this is the, let's say this is the current sheet width A, and this is my x equals 0, right? And the technique that is going forward used to do this analysis is the technique that is used for boundary layers, okay? So the resistivity is really important only near x equals 0. So there is an inner boundary layer where the resistivity is important. So I'm going to call that delta n, okay? And you can see from the linearized equations that they are sort of non-trivial because you have these coefficients which are some functions of x and so on. So going forward, what I'm going to do is basically show you how it is done. So like I said, we are doing boundary layer theory of this. So there is an inner region and there is an outer region. So the outer region, I'm going to just say OR, is a place which is sort of much larger than the delta n, right? And here we are going to ignore inertia and resistivity. So I'm going to not consider it in the outer region. In the inner region, where resistivity is important, we'll have basically gradients which are much larger than the wave number responsible for the growth. Okay, so delta x is going to be much larger than k. Also, in the inner region, we can make an approximation for that f of x that I've taken in the equilibrium. The equilibrium may be like whatever, tan hyperbolic or so on. But in the inner region, I can say f of x is basically x by a. Okay. So the idea is now to solve the equations in both the regimes, and there will be an overlap region where we match the solutions and so on. Okay. So, okay, wait. So let me start with the equations in the outer region. So if I look at the outer region, I'm going to ignore the resistive term and the inertial term. So I get basically phi1 equals psi1 by f of x. And then I have delta x square minus k square minus f double dash by f psi1 equals 0. Here note that f double dash is like the gradient of the current. So that is sort of important. And in the overlap region, so since both of the conditions are valid in the overlap region, on top of this, I'm going to have f of x equals x by a, right? So from this, I'm going to lose this guy, and since del x square is going to be much larger than k square, so then I get psi1 double dash equals 0 in the overlap region.
So in the inner region also you drop this left-hand side, right?
In the inner region?
You drop the left-hand side of the
This one?
equation.
No, I have not yet come to. I have not yet come to inner region.
Oh, you haven't come.
Yeah, outer region.
Everything is for outer region.
This is outer region. Now the overlap region, I'm saying I will take f of x equals this one, and then if I put that into this solution, this equation, then I'll get this. So now I want a finite flux at x equals 0 for this reconnection to take place. So I'm looking for even solutions. So I can write down psi1 is equal to psi1 of 0 plus x, the absolute value of x, into psi1 dash of 0. Okay. At this point, it is useful to define what is known as the instability parameter. So the instability parameter is some sort of a measure of the discontinuity in the initial equilibrium field. So that is known as delta prime and is defined by psi1 prime by psi1 at 0 minus 0 plus. Okay, and from this I am going to get 2 psi1 at 0, psi1 dash at 0 and psi1. Okay, now I will write down the inner region equations, okay, where I will keep all those terms that I neglected in the outer region. So in the inner region, I have psi1 minus x by a phi1 equals a square by eta tau h square, no, tau, okay, I messed this up. So this is gamma tau eta psi1 double prime. So this is my first equation, and the second one is gamma square tau h square psi1 double dash equals minus x by a psi double dash. Right. So these are my two equations. Now if you look at that, then you will see that if you want to solve this, it's basically going to result into some fourth order differential equation for psi, if I were to substitute phi into the other one, right? So it's going to be like a long, tedious process to calculate and so on. The simpler way to do this is to kind of just solve by estimating terms, which is what I was trying to tell you the other day, that there is an easier way to get around to this calculation. So the way to do it is, you say that in the inner region, I will replace the derivatives by psi1 divided by delta, that the width of the current sheet. The other option is to simply say that psi1 prime is delta prime into psi, which comes from the definition of the Turing mode parameter, instability parameter. So if now I use the first option and kind of do these estimates, then I get this. So from the second equation here, I can write down gamma square tau h square phi1 by delta square is delta by a psi1 by delta square. So this gives me phi1 goes as delta by a gamma square tau h square psi1. This is something that I get directly from the second equation. From the very first equation, I'm going to take the first two terms and consider that they are of the same order. So if I do that, right, then I have psi1 going as delta by a phi1, which is basically delta square by a square gamma square tau h square psi1. So then you can see that I can cancel off the psi1 and get delta square by a square goes as gamma square tau h square, right? Yeah, so here I took the first two terms and compared them. Now I can take the first term and the third term, and when I do that, then I get psi1 a square by gamma tau eta psi1 by delta square. So this then gives me, so I take delta square by a square from here, plug it into this, psi1 gets cancelled, so I'll get gamma square tau h square goes as 1 by gamma tau eta. Right, so from this I can actually get now an expression for gamma. So my gamma is going to go as tau eta 1/3 and tau h minus 2/3. Okay, so this is the result that we wanted to come to. And if I kind of reorganize this thing, essentially I'm going to get a by, say, VA s the power of 1/3, minus 1/3, okay? So you can see that, again, the Lundquist number is raised to a power of negative fraction. Okay, so this is, so I have done only the case of this one. So if you use this other kind of estimate, then you get another result, which corresponds to another regime. So what I mean to say is that if with this delta prime parameter, if the delta prime parameter is small, then I get one type of scaling, and if the delta prime is large, then I get the other scaling. But the important point to note over here is that both the scalings have an exponent which is a negative fraction, which means that basically it's going to be a slow kind of instability. Delta prime is the instability parameter. So it kind of tells you, it gives a measure of how sharp is the gradient of the equilibrium that you had taken. So if you have something that's not too sharp, then you are not going to get tearing mode instability. That's the idea.
So basically these are two length scales.
Yeah.
Delta prime and that other delta. And one is just the thickness of the boundary layer.
Yeah.
And the other one is just the slope at 0.
Yeah, you're right. Yeah.
And they could both be the same also,
no? Okay. Yeah, you're right. They could be same, but maybe that will not trigger the tearing mode then.
But this scaling seems to say that there's a connection between that length scale and this length scale.
Yeah, so depending on my equilibrium, there will be a connection. I can write down how delta prime goes as A and so on. Yeah. Right. Is it similar to the? So no, here I'm starting with 0 background velocity. There is no background velocity. No, so I take only perturbations in phi, so there is no mean phi. Yeah. Psi was the vector potential. The phi is is related to the vorticity. Yeah. Yeah, the primes were referring to the spatial derivative. Yeah. Of the equilibrium. The equilibrium, yeah. So, yeah. So this is kind of the dispersion relation that you would get with the different delta prime and so on.
So this expression, psi1 equals psi0 plus mod of x psi prime. It's sort of like a Taylor series expansion.
Yeah, it's just I'm solving this guy over here, right? If I just integrate it twice, the only thing I'm making sure is that it's an even function. Yeah, because we're looking for something where there is a finite magnetic flux at the center. So that's So the plasmoid, now coming to the important part, the plasmoid instability is essentially the same thing, the tearing mode instability on a sweet Parker current sheet. Okay, so where I am requiring this A to be delta SP. Okay, and that's what then leads to like faster. So if I look at the nonlinear regime of the tearing mode instability, what happens is that there are these islands which come up, right? They grow fatter and fatter, and at some point, it undergoes what is known as an X-point collapse to form like a secondary current sheet. Okay, and this is important. I'm telling you because this is the kind of setup that I use in my simulation. So if this secondary current sheet is a thinner current sheet, then you can think of plasmoid instability as a secondary instability on top of the tearing mode instability. but that's an aside. So this is the reconnection phase diagram. So what one does here is basically use magnetic reconnection relevant parameters to map out different plasma regimes and chalk out the nature of the magnetic reconnection in these different plasma regimes. So the y-axis is the Lundquist number, and the x-axis given by something called lambda, which is basically the current sheet length in units of either the ion skin depth or rho s. So now I'm going beyond MHD. Okay, I want to look at stuff which is beyond MHD. So here you can see that this side is basically the fluid side, and this is the more particle-like, more collision-less kind of regime. Okay, and in various places it says multiple X line, which means you can get plasmoids, you can get plasmoid instability. And the places where it says single X line, you cannot get plasmoids. Okay.
That's for linear.
Yeah. So this is your 10 to the power of 4 that I was referring to earlier. So that's this green line comes from there, and this black line is basically when the width of the Sweet Parker current sheet is comparable to one of the parameters, the relevant parameters, which is like the ion scale or something, right? So if the ion scale is larger, then you go into this kind of collision-less plasma regimes. If the ion scale is smaller, then you are in the fluid regimes. Okay. So for example, the solar corona kind of sits here somewhat between the two, and then you have more fluidy stuff like molecular clouds and protostellar disks over here in the fluid regime, right?
So the definition that you did was MHD.
That was MHD.
There are similar things
in the collisionless. Well, similar thing in the semi-collisional regimes, or the hybrid kind of regimes. In collisionless case also you can do this kind of stuff. But there, of course, the inner boundary layer and all will be controlled by other parameters like maybe the electron skin depth and so on.
Lines are obtained from some sort of a dispersion relation or from simulations?
This one is in the collision-less regime. This is like an empirical line, but this line is simply from the fact that if you have Sweet Parker current sheet, and if it is not visible, then you are basically in like the collision-less regime and so on. So you can see that it spans like many decades, but the one that is relevant or is of interest to me is over here, sitting in a very small phase space volume. So I'm going to zoom into that, and then you can see that the area of this phase space volume, which is occupied by these experiments, the amount of area that belongs to the area which is plasmoid fertile is very less. So I can get plasmoids here, but not here, and so on. Okay. So if I wanted to do reconnection experiments and then look at whether I get plasmoids, then the area that is available to me is very small. Right? So this is where the semi-collisional regime comes in. The semi-collisional regime is sort of going beyond MHD. It is collisional. So the time scale that is the smallest is governed by the electron-ion collision frequency. But at the same time, you also have ion scales spatially showing up. Okay. So in the plasmoid instability context, there is like a definitive definition for this semi-collisional regime, where the ion scales come in between the inner boundary layer and the current sheet width. Okay, so if that is the case, then you are in semi-collisional regime. If this rho s is much smaller than delta n, then you are in a sort of fluid regime and so on. So again, you can do the tearing mode analysis for plasmoid instability in the semi-collisional regime, and you get the following kind of scalings. Right? So these scalings are different for different equilibrium and so on. But again, the point to note here is in the growth rate scalings, all the exponents are kind of positive fractions, which indicate that you have this fast reconnection. Okay. The other player that comes into the game is rho s by L. So this is important because combined with the semi-collisional regime constraint, you now get a critical Lundquist number which is scale dependent. Okay, as opposed to like just a set value that was there in the MHD case, which was like 10 to the power of 4. Now you have like a scale dependent critical Lundquist number. So this is great because now if you go to the revisit the reconnection phase diagram, and a window opens up over here due to the semi-collisional regime. So there is a window in which you can get plasmoids now, so which overlaps the experimental phase space. Okay. So at this point, the questions one wants to ask are the following: that indeed, do plasmoids arise at low Lundquist numbers? Because in MHD, you had to go to 10 to the power of 4 or something to get these plasmoids. So can we actually get plasmoids at low Lundquist number? That's question A. And these bounds that are given by the semi-collisional calculation, are they really valid since we are working with some sort of asymptotic theory? So these are the two questions. So the simulations that I performed, this is the sort of setup. It's like a 2D system with periodic boundary conditions. And the way that I obtain my current sheet, which becomes plasmoid unstable, is by that X-point collapse that I had mentioned earlier. Then I'm setting the eta and rho s explicitly. And by modifying delta prime and so on, I can get desirable length of the current sheet and so on. And the resolution is, of course, decided by what is the inner boundary layer width that I need, right? So this is like a schematic to tell you that the simulation that I'm going to show in shortly, what is happening in there, okay? So I initially have a current sheet, which is in MHD regime. And it goes tearing mode unstable. And in MHD regime, basically the inner boundary layer width is much larger than rho s that I have set. Now it goes tearing mode unstable, performs X-point collapse, and there's a secondary current sheet which forms. And the secondary current sheet has a width which goes as the Sweet-Parker scaling. And at this point, the inner boundary layer of that current sheet is smaller than the rho s or the ion scales, okay? And we have entered the semi-collisional regime at this point. And then a plasmoid forms and so on. So this is like a simulation of what I just described. So initial equilibrium and tearing mode takes place. So you have an island and then the secondary collapse happens and then a plasmoid arises. So it's like really happening very quickly. So the linear regime itself is very, very, very short-lived. So what you are seeing is actually the non-linear regime where the things fatten up and then the secondary collapse happens. So that's all happening I mean, pretty quickly in the sense that the color coding is essentially the yellow is going to be the stronger magnetic flux contour.
Magnetic field strength.
Yeah, the magnetic field strength. So yellow is generally strong. So then you have this plasmoid that is coming up in the semi-collisional regime, right? So
magnetic hole where there is within the plasmoid, magnetic field is weak.
Inside, right inside the, yeah. So there are because just right there is where the current sheet is, where you will get the null point where the magnetic fields are cancelled out each other, right?
Length scale seems to be determined by the previous instability, no? In this case, like the first instability made this long length, and then the plasmoid thing just chose that as the length scale.
Correct, but we are fixing the length and the rho is such that it's amenable to being in the semi-collisional regime. So this plot is kind of the main result of the simulation work. So what I show is the semi-collisional regime given by these two bounds. And beyond, over here on the left is the collisionless regime, and on the right is the fully collisional MHD regime. And this is the semi-collisional regime. And the stars mark the simulations where we did see plasmoids, and the inverted triangle and diamond is referring to the case where there were no plasmoids. Actually the equations here are what are known as reduced gyrokinetic equations. So it comes first from the distribution function kind of formulation where you have like the Boltzmann type of equation, and then on top of it for the plasma, for kinetic plasmas, and then you do a closure which brings it to this semi-collisional regime. So it's some sort of reduced version of kinetic equations, but essentially what finally they encompass is some two fluids kind of effects. Yeah, so it is something similar to that. So you get your first moment and second moment, and then there is a reduced distribution function. In that reduced distribution function, again you are choosing only certain, you're going up to only certain order in the velocity coefficients. And you are kind of doing this closure so that you retain only terms which are relevant to the semi-collisional regime, and so on. So those are the equations that I'm solving.
So basically, plasma.
Yeah.
That's the.
Yeah. Yeah. Right. I mean, basically, yeah, they are all being solved self-consistently. Yeah. So what happens is you have electrons and ions to begin with. Then, because we are in the semi-collisional regime, we keep only the terms which have the ion scales showing up in them. So the electrons are not, they are like fluid Z. So here the important thing to note is that the simulation at the lowest Lundquist number that I could go up to is about 250. So in MHD, you had to have 10 to the power of 4 to get plasmoids, as opposed to this semi-collisional regime now, where I can get plasmoids at already Lundquist numbers of 250. like really small Lundquist numbers. So that's why this regime is nice, because it's experimentally accessible. So the other question one can ask is if the current sheets that I did obtain from the secondary collapse were Sweet-Parker scaling or not. And the answer essentially is yes. In the case of semi-collisional and MHD case, you would get the scaling, and the collisionless, you wouldn't see it. Okay, I'm just going to go further. So the one peculiarity that we did see in all these simulations is that there was a plasmoid. Okay, so since we were ranging from 250 to Lundquist number of 5,000, so we were going to really large Lundquist numbers, my Kmax scaling would have predicted seeing many plasmoids as opposed to only one single plasmoid. So in our simulations, however, we saw only one single plasmoid every time. Ah, okay, right. Yeah, so there was only one single plasmoid, and we think that is partially due to the way the secondary collapse happens, and there is probably no time for other plasmoids to come up and so on. But what we found is that if we look at the y extent of the plasmoid, which is another way to kind of get the wave number, that actually scales as what the linear theory predicts. So that sort of kind of reaffirms reassures that we are in semi-collisional regime. So we can ask now that, have we seen these in experiments? Right, so there is an experiment in Imperial College in London called MAGPIE, where they have seen plasmoids, and this is like a tentative thing. But let me briefly describe the experiment to you. So they have these magnets here, and surrounded by carbon wires, and these carbon wires are ablated, so they form plasma and carry the reversing magnetic fields towards each other, and there is a reconnection layer that forms, and they look for plasmoids in this reconnection layer. And what I show over here are electron density maps they get from laser-based instruments, and they can get lineouts from the reconnecting layer, and in the lineouts they see several bumps, which is indicative of potentially plasmoids that are coming up in the reconnection layer. So all of this happens at like really fast time scale, so you kind of see this at all nanoseconds and so on, right? And the important thing is that if you were to estimate the Lundquist number and the L by rho s for the plasma seen in the simulation, those parameters simply fall into the semi-collisional regime. So what we think is that the plasmoids that are being seen here are being seen essentially because they fall into the semi-collisional regime. Of course, they did not go beyond this to kind of test out the boundaries of semi-collisional regime and so on, because our paper did not come out up until after this experiment. So they could have potentially done that to kind of make sure that these are the semi-collisional plasmoids that one is seeing. So, right, so this is sort of experimental evidence for plasmoids that could come up at low enough Lundquist numbers. So with this, I end my talk. And the summary is that we have explored and studied the semi-collisional regime for plasmoid formation and we have validated it in the phase diagram, reconnection phase diagram. And we find that there are plasmoids which arise at low values of Lundquist number and could potentially explain the formation of the plasmoids in some recent experiments. Some of the future things that I want to look at, as you would have noticed throughout my entire talk, all the magnetic reconnection models that I have shown you were essentially 2D in nature. And what one wants to do is go beyond 2D and look at 3D reconnection. And it is also important to understand the interplay with turbulence, because most plasma that we have in astrophysics are of turbulent nature. So how does reconnection interact with the background turbulence and so on? That is another thing to look at. The other work that I didn't talk about is the role of reconnection in 3D non-helical decaying emission turbulence. So one wants to kind of look at better models to understand that in the future. And of course, there will be continuous effort to identify different astrophysical scenarios where reconnection can explain the observables. Thank you.